Okay, so far in Chapter 8, we've learned how to multiply, divide, add, and subtract rational functions. Today we're going to learn how to graph rational functions. So, a rational function has an equation of the form, since it's a function, it's going to start with f of x equals p of x over q of x, where p of x and q of x are polynomial functions, and q of x does not equal 0, because again, we cannot have a denominator of 0, or else that makes it undefined. Now, when we're graphing these, there's a couple of new things with graphing that we're going to learn about here for graphing asymptotes, or for graphing rational functions, sorry. The first one is an asymptote. We have both vertical and horizontal asymptotes when we're graphing rational functions. And those are lines that the graph of a function approaches but never touches. So what that looks like, if I've got my coordinate plane, I'm going to draw in the red dotted lines are going to be a horizontal asymptote and a vertical asymptote. And then our graph would look something like this with our blue lines. So it would be two curved lines that approach those dotted lines, the vertical and horizontal asymptote, but never actually touch them. Then we have point discontinuity, which is a hole in a graph. So what that would look like is if we graph a line, it would go to there, then we would have a hole in the line, and then the line would continue from that hole. So in other words, what we're really talking about is any point on that line would be a solution to our rational function except where that hole is. It's kind of like when you graph on a number line. If it doesn't include equal to, then you use an open circle, meaning that that point is not included in your solution. So the first thing we're going to do here is learn about vertical asymptotes. If the rational expression of a function is written in simplest form and the function is undefined for x equals a, then the line x equals a is a vertical asymptote. So simplest form, that means everything is factored as much as possible. So for this one, we have f of x equals x over x minus 3. That's its simplest form. Everything is factored. Nothing can be canceled there. So we would take whatever is in the denominator and we would set it equal to 0, which would give us x equals 3. So that means x equals 3 would be a vertical asymptote, which means on our graph, we would have a vertical asymptote at the point x equals 3. So we would go to 3 on our x-axis and draw in that dotted line representing the vertical asymptote. Next we have point discontinuity. So this is where if the original function is undefined for x equals a, but the rational expression of the function in simplest form is defined for x equals a, then there is a hole in the graph at x equals a. Now, that's a lot of words and a little bit confusing. The simpler way of saying this is that if you get your rational function factored as much as possible, so here x plus 2 times x minus 1 over x plus 2, this can still be simplified by canceling our x plus 2's, which means that the graph is simplified to f of x equals x minus 1. So anything that is canceled from both your numerator and your denominator, you will set equal to 0. So x plus 2 equals 0, x equals negative 2. So in this case, since it was canceled, that point of x equals negative 2 would represent a hole in the graph. So what that would look like, if I get a graph on here, Sorry about this, thought I had it on there already. So if I get my coordinate plane on there, I'm going to graph my function that was simplified to f of x equals x minus 1. We can think of that as y equals x minus 1. So when we graph that, we've got a y-intercept of -1, and we have a slope of 1. But we know that there is a hole in the graph at x equals -2. So at this line right here, we're going to have a hole in the graph. So as we continue marking those points, when we get to x equals -2, we're going to have an open circle. So our line would look like that with that point of discontinuity at x equals -2. So, limitations on the domain, that's where we're talking about our vertical asymptote and our holes. So determine the equations of any vertical asymptotes and the values of x for any holes in the graph of each rational function. So when we do this, our answer for this, we just have to give what the vertical asymptotes would be and what the holes would be. Those will both be written as x equals equations. So in order to do this, the first thing we need to do is factor this as much as possible. X squared minus 1, we've got a difference of squares. So this will factor out to x plus 1 times x minus 1. In the bottom, we need to come up with two numbers that multiply to 5 and add to -6. That would be x minus 2 and x, sorry about that. I was thinking multiply to 6, add to 5. Multiply to 5, add to -6 would be -5 and -1. So x minus 5 times x minus 1. So here, our x minus 1's can cancel, meaning that that is going to represent a hole where we would say x minus 1 equals 0, so x equals 1. So we would have a hole at x equals 1. Then anything that's left in the denominator and can't be canceled would represent a vertical asymptote, which would be x minus 5 equals 0, or x equals 5. So for this one, we're not graphing or anything. They just ask us to determine the equations for vertical asymptotes and holes in the graph. Which again, because x minus 5 is not canceled, that's left in the simplest form, then that would be a vertical asymptote. Because x minus 1 is canceled, that would represent a hole. Let's do one more here. This is going to become, we need two numbers that multiply to 8, add to 6. So x plus 4 and x plus 2. This is a difference of squares. It'll come out to x minus 4 times x plus 4. So now we can cancel the x plus 4's, which since that's canceled, that becomes a hole. X plus 4 equals 0 would give us x equals -4. X minus 4 is left, it's not canceled, so that's going to be a vertical asymptote. X minus 4 equals 0 would give us an asymptote at x equals 4. And that would be our solution there. So now that we've learned how to find those, we're going to go ahead and actually graph. But before we graph, we've talked about vertical asymptotes. Now we need to look at horizontal asymptotes. In order to find those, we're going to take the ratio of the leading coefficients of the numerator and the denominator, If there is no x value in the numerator, the horizontal asymptote is at y equals 0. Now, we want to wait to look at that ratio until we get our function down to its simplest form. So here, f of x equals x over x minus 2. So we want to figure out, first of all, can this be factored? No, numerator and denominator are both factored as much as possible. There's nothing that can be canceled. So this is in its simplest form. Since nothing is canceled, that means there will not be a whole. There will be a vertical asymptote where we would do x minus 2 equals 0. So then x equals 2. So again, we have a vertical asymptote at x equals 2. So we can go ahead and draw that in, represented with a dotted line there at x equals 2. Then we need to find our horizontal asymptote. A horizontal asymptote will be in y equals form because horizontal lines are always y equals. Now we take the ratio of our leading coefficients. Again, the leading coefficient is the number in front of the highest value of x. So here leading coefficients are both 1. Ratio 1 over 1 is 1. So our horizontal asymptote would be at y equals 1. So we've found our horizontal and vertical asymptotes. Now we need to graph our function. So in order to graph our function, we're going to make a table of values. And what we want to do is we want to use 3 points to the left of our vertical asymptote and 3 points to the right of our vertical asymptote. So my 3 points to the left, I'm going to use -1, 0, and 1. 3 points to the right, I will use 3, 4, and 5. So now I just plug in my x value in order to get my y value. So -1, I'm going to get -1 over -1 minus 2, which will give me -1 over -3, which is positive 1/3. Since a negative divided by negative is always a positive. So I'm going to have a point at -1, 1/3. So -1, 1/3. I'll have a point right there. Plug in 0. I get 0 over -2, which is 0. So I'm going to have a point at 0, 0. Then when I plug in 1, I'm going to get 1 over 1 minus 2, which is -1. 1 divided by -1 is -1. So that's going to be my graph to the left of my vertical asymptote. To the right, plug in 3, I get 3 over 1, which is 3. So I have a point at 3, 1, 2, 3. Plug in 4, I get 4 over 2, which is 2. So I'm going to have a point there at 4, 2. And then plug in 5, I get 5 over 3, which is 1 2/3. So 5, 1 2/3. So this would be the graph of this rational function. Again, our steps there, we found vertical and horizontal asymptotes. We would find our holes if there were any, put those on the graph, and then make our table of values. Let's walk through one more of these here. So here we want to get it to its simplest form first, which there's nothing we can factor here. There's nothing that can be canceled out. Since there's nothing canceled, that means there will not be a hole. So we know we'll have a vertical asymptote at x equals something and a horizontal asymptote at y equals something. So the vertical is where I take whatever's in the denominator and set it equal to 0. So it's going to be at x equals 1. Go ahead and graph that on there. Then my horizontal, again, is the ratio of the leading coefficients, which is 1 over 1. So horizontal, again, is going to be at y equals 1. Now I make my table of values. 3 points to the left of my vertical asymptote, which, sorry, will not be -1, 0, and 1. In this case, will be -2, -1, and 0. Then my 3 points to the right, which will be 2, 3, and 4. So I plug in -2, I'm going to get -1 over -3, which is 1/3. Plug in -1, I'm going to get 0 over -2, which is 0. Plug in 0, I'm going to get 1 over -1, which is -1. Then plug in 2, I'm going to get, 3 over, plug in 2, I'm going to get 3 over 1. Plug in 3, I'm going to get 4 over 2, which is 2. Plug in 4, I'm going to get 5 over 3, which is 1 2/3. So you'll see here, we ended up with the same y values on both of these. That will not always happen. It just happens to be true here. So now we're going to graph our points. -2, 1/3. -1, 0, and 0, -1. Go ahead and graph that curve. Then 2, 3, 3, 2, and 4, 1 2/3. Missed my dots a little bit, but that would be our graph for that rational function. We've got one more slide here, a couple more graphs that we're going to do. So on this slide, we're going to be doing graphing with point discontinuity. So, graph each function. Again, first thing we always want to do is get it to its simplest form. So x squared minus 9, difference of squares, would become x plus 3 times x minus 3 over x plus 3. Those cancel. So our function in its simplest form would become f of x equals x minus 3 over 1, or just f of x equals x minus 3. Now, since our x plus 3 canceled, that means we are going to have a hole in our graph at x plus 3 equals 0, or x equals -3. So now that's all I have to do. I can graph this now. I can think of this as slope-intercept form. Y equals x minus 3. So I'm going to have a y-intercept at -3, and I've got a slope of 1. So I know I'm going to have a hole at x equals -3. So if I go ahead and do my slope of 1, I'm going to have a hole there at x equals -3. So my line would go there and continue on that side. So our solution to this function would be any point that falls on this line except for that point at -3, -1, 2, 3, 4, 5, 6. So that's where we have just a hole in the graph. The next one that we're going to do, we're going to end up, this one we only had a hole because there was nothing left in the denominator in our simplest form. This one, we're going to look at a little bit different scenario. We want to get this factored, so we're going to have x plus 3 over two numbers that multiply to 12 and add to 7 are 3 and 4. So x plus 3 times x plus 4. Now here, our x plus 3's cancel, and we're left with our simplest form of 1 over x plus 4. So what this means, we had something that canceled, which means we're going to have a hole in our graph at x plus 3 equals 0 or x equals negative 3. Then, because we still have something in our denominator here, that means we are also going to have a vertical asymptote on our graph, which will be at x. So the x plus 3 became our hole. The x plus 4 becomes our vertical asymptote at x plus 4 equals 0 or x equals negative 4. So negative 4 is here. I'm going to go ahead and draw that vertical asymptote in. Then I need to figure out what my horizontal asymptote will be. Remember, the horizontal asymptote, once you have the function to its simplest form, is going to be the ratio of the leading coefficients. Now here there's no x value, so there's no leading coefficient in our numerator, which means it'll be 0 over 1, which is 0. So our horizontal asymptote will be at y equals 0 or on the y-axis. So now that we have all of that on there, we need to make our table of values and graph. So 3 points to the left of my vertical asymptote would be 1, 2, 3, 4, so 5, 6, and 7, negative 7, negative 6, and negative 5. My 3 points to the right would be negative 3, negative 2, and negative 1. Now I'm going to plug my numbers into my simplified version. I don't need to plug them into the long one that I started with. So plugging in negative 7, I would get 1 over negative 7 plus 4, or 1 over negative 3, so negative 1/3. Plug in negative 6, I'm going to get 1 over negative 2, which is negative 1/2. Plug in negative 5, 1 over negative 1, which is negative 1. I'm going to go ahead and graph those 3 points. So negative 7, negative 1/3, negative 6, negative 1/2, and negative 5, negative 1. So that's that side. Plug in negative 3, I'm going to get 1 over 1. Negative 2, I'm going to get 1 over 2. And negative 1, I'm going to get 1 over 3. Now, when I graph these points, I have to remember I had a hole at x equals negative 3. So my point negative 3, 1, since that's at x equals negative 3, I'm going to graph that point, but it's going to be an open circle because there's a hole at that point. Then negative 2/2 and negative 1 1/3. So it'll look like that with that open circle or that point of discontinuity at x equals negative 3. So again, just as long as you follow those steps in the right order of how to do these, you'll be good to go. You can always go back, watch this again. If you need to, you can go look on Khan Academy or look up other videos on YouTube. Reach out to me if you need help. You do have a short assignment today since each step or each problem has multiple steps and some graphing involved. So you're just doing numbers 1 through 8 on page 460. For this one, you're going to need to do it on paper and turn in a picture of that instead of just submitting your answers as a Google Doc because of having graphs. So go ahead and do that. And again, please reach out if you need any help at all on this. We've just got a few weeks, about a month or so, a little less than a month left that we're going to be doing lessons. So make sure you're finishing strong, getting anything in if you're missing anything. And yeah, let's just finish this year strong.